An operational amplifier, or OPAMP, is an electronic device that amplifies the voltage difference between its two inputs, the inverting input and the not-inverting input. But hey, this sounds kind of difficult, so let's start with the parts. I already mentioned the inputs. Now there's the output voltage and there's also the power supply, because without this it doesn't amplify anything. This can be plus and less 15 or more or less 12, as you prefer. Also, let's talk about ideal resistors, in which the input is infinite so it doesn't consume current from the input signal, and the output resistance is 0, which allows the enter signal to be delivered to the load without loss. We can memorize it like this. An ideal op-amp looks at the input without disturbing it and pushes the output with full force. This is a non-inverting amplifier circuit characterized by having the input signal connect to the not-inverting terminal. This indicates that the gain will be positive, unlike the inverting one. First, we see that Vx, the voltage at the negative input, is equal to Vin, now as the closed loop principle. Since the input current I1 is practically zero, the current through R1 is equal to the current through R2. That is, current R1 equals current R2. Now, let's define how to find the gain. As we mentioned before, the currents of resistance 1 and 2 are equal to applying Ohm's law, leaving Vin minus 0 over R1 equal to Vout minus Vin. Remember that Vx is equal to Vin. Over R2 we multiply crosswise so that we have R2 over R1 equal to Vout minus Vin over Vin, and from that we take the common factor, which is Vin. We pass the 1 to the other side to add leaving Vout over Vin and the other side, which is the gain. And to get Vout, the Vin is passed to the other side to multiply. First, we will take out the LM741 amplifier. It is taken from the figure that says place analog. Now, to take to the voltage source, we go to the same row on the left and look for something that says place source in signal voltage source and AC voltage. We will hit OK. For the resistors, in the same row, we look for the figure that says place basic, resistors, and the ideal for 1000. We take out another equal resistance, and in the group we go to the power sources, we choose ground and OK. We do this 2 more times, once for the alternating source and another for one of the resistors. Then, to take out the power supply and call DC power, we take out 2 on the right side. The 4th item, you click to take out the oscilloscope. Now that we have the elements, we can make the connections. The AC voltage source, the negative side, we connect to ground. The resistance 1, we connect to the ground. We join the power supply, and in the middle, we connect the ground. Resistor 2, we connect to the negative side of the amplifier. Remember that the AC power we connect to the positive amplifier side, and then the output of the amplifier connect the other one to the resistor 2 and resistance 1 at our end. Then on we connect the positive side of the source as shown, and on pin 4 we connect to the negative side of the same way. Right. The oscilloscope, we connect pin positive to voltage out, or the voltage another the same way to show. Then pin B positive to the non-inverting input, and the negative side of the pins to ground. We convert AC by doubly clicking at a frequency. of more or less 500 hertz. Then click OK. We double click on the oscilloscope and so we see the wave. We click on those cursors that appear in the upper left to see the peaks, and if it's necessary, we click and put the go to max or min and. That is why. So we can see that channel A, which is the output, has double the input channel A.
The second configuration is the subtractor. It has two pairs of equal resistors. One pair corresponds to the inputs and the other connects Vx to Vout and Vx to ground. Due to the virtual short circuit, the inverting input node has the same voltage as the non-inverting input. By the voltage divider principle, this voltage is defined currently. According to Kirchhoff's law, the current flowing through the second input, resistor 1, resistor 2, and the output voltage is the same. The current is defined as the voltage difference between the positive and negative nodes across each resistor are therefore equal. The denominator is then distributed across the sum of the numerators, giving the intermediate result. A common factor is extracted, and after solving the expression, both the gain and the equation for the output voltage are obtained. The setup includes the power supply, the set of two pairs of resistors, and the sources to be subtracted. The loop is connected from ground to the non-inverting terminal and resistor 4. Then the inverting input is connected to their second term and negative feedback. Next, the positive terminals of the oscilloscopes are connected to the output and the input, and the negative terminal is connected to ground. Note that the output voltage cannot exceed the supply voltage. When simulated, a maximum input value in V is obtained, whose difference from the other 10-volt source is what is shown on channel A.
2 hours later.
The third configuration is investor weighted adder. This consists of a resistor between the inverting terminal and the output, and any inputs with n resistor. Since it is an inverting configuration, the non-inverting terminal is connected to ground. Due to the virtual short circuit, the nodes at the inverting and non-inverting inputs are equal and correspond to 0 volts. The current through resistor 1 is equal to the current through resistor X, given this equation. As Vx equals 0, it is replaced in the expression, obtaining the output of V1. However, in this configuration, the total output will be negative of the sum of individual outputs, since the gain of each output is the ratio of the resistance Rx over Rm. A weighted average is obtained.
Bye, bitch!
We observe the plus minus 20-volt supply, a set of resistor and input voltage, and the ground connection at the non-inverting input, since it is an inverting configuration. In this example, we use 4 inputs, each with a value of 0.25, similar to a total grade composed of 4 individual scores of equal weight. This produces a circuit in which each input is multiplied by 1 across 4, resulting in an output of 5 if all inputs are 5, as you can see. Note, the symbol is negative. If any of the inputs is changed, the output decreases accordingly. Finally, the circuit is modified again.